Have you ever seen these YouTube shorts where kids or teens drop these insanely fast line follower robots that follow the most optimal line path and at speeds that make you think, is that line following in real time? Well, I have, and I'm sure you probably have, or might have. I want to see if I could actually build my own and reach short levels of performance. Note, I did see comments saying that the line followers on these competition maps already have a round where they go through the track slowly and then find the shortest possible path. But nonetheless, I present to you Unnamed, the phase 1 of my speed demon line follower robot I am developing. Yes, I know, it's slow as hell, but let me explain. It's unnamed because it's slow and was simply a test platform built to implement motor speed control, PID loop control, sensor tests, and overall, just like I said, a phase 1 test platform where I can explain all the concepts fully. In this video, I'll be going over how I got to the fully working test platform in the 6 or 7 days of semi-consistent workflow it took to build.
Stop it. Get some help.
I'll go over the line detection principle, sensor selection process, line size consideration, the position calculation, line following algorithm, and PID control loop. Ironically, for someone who has built over 15 projects this year alone, for some reason I have not built a line follower robot before, until now. And as an engineer, I decided to pick a speed demon as my final goal because why not choose your suffering and make it worth it, or make a video from it. With that, let's get right into the building process. For phase 1, let's talk about how line following robots actually work. First of all, the robot needs to be able to detect the line, right? But these particular lower cost robots aren't running on cameras using computer vision to detect the lines. So what sensors do they rely on? Infrared based sensors, commonly called IR sensors. These robots rely on simple infrared sensors which you can buy either as a single module or an array which contains several in a straight line, curve, or a particular shape based on the need. I'll talk about the advantages of shapes later in the video. These sensor modules can have digital outputs which are gotten from a comparator using an op amp and can be calibrated using a potentiometer to give a high or low response, or they give analog voltage output, and quite some I've seen have both. An IR sensor contains an IR emitter which, like the name implies, emits infrared rays onto a surface. The receiver, on the other hand, allows a current to flow based on the intensity of the reflected rays received, which is then based on the distance from the surface features like color, material, and other factors such as emissivity, reflectivity, and transmissivity of the surface. By taking measurements from the sensors, one can detect the presence of an object, distance, and colors from these IR sensors. This allows the use of one or more sensors to detect a background color and the color of the line. You may ask why these tracks use white backgrounds with black lines and vice versa, but before I answer that, I want to say Merry Christmas and Happy New Year. Compliments of the season to everyone and to all my subscribers. We were able to reach 600 subs this year, not the goal of 1k, but nonetheless, even with my bad upload schedule, I'm grateful to every one of you. And if you haven't joined the community yet, why not go ahead and hit that subscribe button as a Christmas gift to me while I provide you with more build videos as mine to you. I have robots in the works, Saber, the self-balancing robot which is done, a hexapod, and a 6 degree of freedom robotic arm, all long-term projects I've been working on. So if you want to see more content like that, why not subscribe and leave a like. Turn on post notifications too if you want to actually be aware of when I post next. Once again, compliments of the season. I hope you had a great Christmas and a new year ahead. Let's get back to the video. The reason for using such high contrast colors like black and white, or vice versa like I was saying, is to get the best readings. White is the direct polar opposite of black, meaning the readings between these two colors are the best possible minimum and maximum, maintaining a huge difference or delta between the two. It prevents your device from the mistake of taking the black color as the white because of how much of a difference in reading values is between the two of them. Such a mistake can occur if you use two colors that give you similar readings that are similar in range and can potentially overlap due to noise in the reading of the signal. Now that we can detect the color of the line and differentiate between it and the background, how do we now follow the line? You can have one sensor that reads the black or white line, and when it detects the inverse background, your motors exert the appropriate turning motion to keep it on track. You can also have two sensors measure the background on the lines left and right, and if the sensor detects the line, the motors apply the appropriate turning motion to keep it on track. This is a closed-loop system where you are constantly using feedback to adjust the response. The most important thing is the number of sensors, distance between the sensors, and the width of the line. Now let's talk about deadband. A deadband is the range of input for which there is no response. By what I mean is, assuming you have a line that has a width of 2 centimeters, your robot using one sensor following the line can only move left or right by 2 centimeters or under pretty much before correcting itself, as it will then cross the line boundary into the inversely colored background. This gives the robot some leeway to move without unnecessary rapid response within 2 centimeters. But this can be a problem. For example, if you want to have more content like this where I build robots and explain the processes, why don't you subscribe? What are you waiting for? Now, assuming the same one sensor scenario, but instead your line is 5 cm wide, that means that your robot can sway for up to 5 centimeters from left to right before correcting itself, and that isn't really a nice response. With such a huge deadband, the responsiveness is then slow. This applies to 2 or more sensors where you would optimally want the width of your line to be equal to or less than the distance between 2 sensors. The more distance between the 2 sensors and the edge of the line, the less sensitive the robot is. This is crucial if you are designing your own sensor array or want to decide the line width. You want a situation where the line can be detected by a sensor at all time. Now, what if the robot is moving at high speeds and the line is lost because you use just 2 sensors or there's a complex root curve? To solve this, use more sensors. I know, right? Quite simple. If you use more sensors over a larger length and use curves to detect the lines that sharply turn off, then you'll be able to solve the problem of easily missing out the line. Ultimately, the best configuration depends on the specific sensors, distance between sensors, width of the line, the speed of the robot, the complexity and sharpness of the curves of the track, and the control algorithm used. With all the concepts out of the way, let's look at my own setup. To summarize, I designed Unnamed to use an 8 IR sensor array I found that would work with a line of width around 15 to 18 millimeters quite nicely, while at the set middle point, the line would be in the middle of 2 sensors at once. In order to find the position of the line, I decided to use a weighted average that would convert the sensor readings of each of the 8 sensors to a range of -40 to 40. This would allow me to take readings on startup and calibrate the setup of any background and line automatically. With the position of the robot being detectable, I would implement a suitable control algorithm. For the control algorithm, I chose a PID controller as I intended to put the final robot through a complicated path to stress test it as much as I could, which might have been ambitious for this particular build, subtle foreshadowing. The other option would be a simple bang-bang controller. In this video on Rovi's channel, he demonstrates the bang-bang controller on a line follower quite nicely, and you can see the distance between the 2 sensors affecting the responsiveness of the robot. On the topic of PID, several channels have covered it much better than I can, and I particularly like the video from DigiKey, which I will link below. But to summarize, P for proportional controller. This is the value gotten by multiplying the gain value Kp you set with the error. Now, error being the difference between the set point you want to achieve and the actual point you are measuring. P is responsible for system responsiveness and steady-state error. A higher gain increases responsiveness but can also increase overshoot and instability. And by steady-state error, it is the inability of your system to reach the exact set point. Just go over the other videos, no need to dwell on that right now. I for the integral controller. This is the value gotten by the accumulation integral of past errors multiplied by a gain value Ki you set. I is responsible for eliminating steady-state error I spoke about earlier, ensuring that the system eventually reaches the exact target set point, but it can create overshoot and reduce stability if tuned too aggressively. And finally, D for derivative controller. This is the value gotten at the rate of change derivative of the error multiplied by a gain value Kd, which you set. D is responsible for dampening the system response to changes, reducing overshoot and improving stability, but can make the system more sensitive to noise. With the basic concept explained, is building time. For the building process, after soldering and soldering and soldering and soldering and finally some more soldering, I was able to make a 2S typo battery pack using 2 18650 batteries in series hooked up to a 2S BMS, which was connected to this 2S charging module that's capable of using a Type-C input. The whole point of this was to test the setup I planned on using for my hex support ahead of time. But because I wanted an easy to use and easy rechargeable battery pack, I went with this method where you can use a Type-C port to actually charge your batteries for your robots. Now, this is still under works. And with the battery pack wiring done, I've changed focus to the chassis. Since this was a test platform, I used the generic acrylic chassis kit with these geared motors. At the front of the chassis base, I screwed in a small caster wheel, And with that done, the next thing was the sensor mount, and this was crucial. The IR sensor datasheet suggested an optimal distance of 3 to 5 millimeters from the surface, which is really small. So I measured the dimensions of the 8 IR array and distance from the ground to the chassis. With those dimensions, I 3D modeled a mount that had screws for the 8 array IR sensor, and at the same time, I also made a small case for the battery pack. After printing the battery pack case, I made a temporary hold on it using tape to just run tests easily. I disassembled the motors to add wiring to them and couple them back. These bronze standoffs were added because I realized I would need more space for the circuit board at the top of the device. A simple motor running test was done, and I confirmed that both motors were running just fine. The next thing I had to do was to start putting all the electronics together. I soldered all the 10 wires I needed for the IR array and added a lot of length to them. I printed the IR array sensor mount, of which the first one didn't fit properly, like almost everything in this space. Then I made some adjustments to the height of the mount and got a proper fit. Screwed them in and screwed them onto the main chassis. With these parts done, I focused on the main circuit board and the main microcontroller, which is an ESP32 dev module. I had an LM2596 buck converter, a TB661 FNG motor driver, and a bunch of headers to enable ease of connection. But during testing, I had a very odd issue where the motor driver would not drive more than one motor at a time on one channel and was refusing to work on the two channels at once. Despite trying the same control signals as the inputs on both channels, I could not just get it to work. So I placed a second motor driver which had the same issue and used just one channel for both, and that seemed to get it working. After soldering the wires for the IR array onto the headers, I started running code and tests. Now, editor me here, it might have been the threshold voltage I was trying to use, which was 8.4 volts from the two batteries, but these motors are supposed to be able to run from around 3.6 volts, and the TB661 FNG does not have an inherent voltage drop that I was aware of. It was just kind of confusing, but let's get back to it. After soldering the wires for the IR array onto the headers, I started running code and tests. First thing I did was to make sure I could get readings from the sensors, which worked great, and then I tested readings on the two different colored sheets of paper. In the process of developing the code for the calibration process and activation for the robot, I added two switches, which one is a power switch and the other is a logic switch for the robot activation. I also added 3 indicator LEDs, which I will explain how they work later, and at the same time added a battery indicator and drilled a hole to mount the circuit board. Yeah, a lot of additions. Unfortunately, while working, the power supply station in my state did what they do best, and I had no power supply. But here's some footage of that too. Yeah. I set up the mat and decided to let the robot take a rip. Following the previously stated logic of how the robot would work, I programmed it to have 2 sensors at the center of the black line, while the others detect the white background as its target set point. Here's the full process of how it works. You put on the robot with the power switch, then immediately the red light comes on. You then set it on the all black surface and press the logic switch to start the calibration process. The robot then takes an average of 1000 readings, and only the orange LED is on during that process. Once it's done, only the red light LED comes on while the robot turns to the all white surface, where the orange LED comes on again and it does another average of 1000 readings. That way, it knows what's the correct set point by having the readings of each sensor for white and black surface. With that done, then the red and green LED come on, indicating that the robot is ready to be set on the line. Once you set the robot on the line and then press the logic switch again, the robot starts the control loop and line following algorithm with only the green LED on. Here's the robot's first ever try on the track, and of course, it starts and fails to follow the line on the first try. Yeah, skill issue. And off camera, I did a bunch of tests, and it was quite perplexing because of the number of issues that kept on coming up. First of all, the two motor drivers were misbehaving with power sharing and were just unable to turn properly, so I swapped them for the single L298N motor driver. Even I didn't want to use it initially because of the 1.4 to 2 volt drop, giving my motors less voltage than I actually would want. Now, with that change made, I realized that the robot wouldn't move at lower voltages where I expected it to on my own PWM control, as I wanted to start with the slowest speeds possible. So I tried using my two 10,000 mAh Lion batteries I got from my hexapod, and those worked, but it was also slow, but this time it actually moved, and one of my batteries actually got bad. But leaving that aside, I bought some new LiPo batteries and changed to a 3S battery setup for higher voltage. After adjusting my P value to allow enough turning force and adjusting a little D value to smoothen that movement, the robot worked. Although on this new track, which I used some tape to make instead of the initially complex track, and that was because I realized that these motors weren't built to perform the way I wanted them to, especially with sharp turns. A low value base speed would mean that the robot would move more slowly and react better, but a higher value would mean that the robot could speed past the line, and to counter this, the P value would need to be higher, which these motors did not like at all. In the end, I tuned it to be able to turn aggressively enough at the sharper turns, but not too high that it oscillated. My main limitation on pushing the speed were these bad performance of these motors. They really had shitty torque, so in the actual speed demon build, I'll be doing things differently, which would be using a different set of motors, a much nicer form factor, better batteries, and even more refined code and settings, in order to conquer a much more complicated track with the main goal of hitting speeds that are actually worthy of the name Speed Demon. And with that, thank you for watching. Compliments of the season once again. Subscribe, leave a like, put on that post notification. See you in the next video.
Thank you for subscribing.